1998 essay paper, question number 2, part A. Right. So this question goes with Bernoulli's theorem. So the first part asks, write down the Bernoulli's equation for a fluid flow. Clearly identify the symbols used. What quantity does each term in this equation represents? State the conditions under which Bernoulli's equation is valid. Right. So this is the theory part of the question. So we'll see how to write the answer for the theory part. This is the Bernoulli's equation. P plus half rho u squared plus rho gh is equal to K. Here K is a constant. P is known as the static pressure. Of the liquid. Rho is the density. U is the velocity, or we can say speed of flow. G is gravitational acceleration. H is height, you can say it's the height from potential energy zero level. Potential energy zero level, and K is a constant. K is a constant. Right. And they also want us to identify the terms here. Now here we have identified the symbols, and they also want us to identify the terms here. So how do we identify the terms? Right. P is static pressure. We have identified the term. And half rho u squared. Half rho u squared. This is known as kinetic energy per unit volume. Kinetic energy per unit volume. You know, this equation, Bernoulli's equation, is an equation of energy. So this is kinetic energy per unit volume. So rho gh is known as potential energy per unit volume. So you can easily get how you got these equations. When you have half mu squared, when you divide by the volume, this becomes density. So this becomes half rho u squared. When you have mgh, this divided by the volume, this becomes density. So it becomes rho gh. Right, so this is an energy equation. So this is how we define the terms. Also, we can write P here as well, since they have asked the meanings of this. So we can say it's the static pressure of the fluid once again. So since we have written it, they also expect us to write it again, right? Right. And they also want us to write the conditions of validity for this equation, Bernoulli's equation. So under what conditions, let's say it is valid. So for this to be valid, the flow must be a streamlined flow. streamlined flow. And also has to be a steady flow, steady streamline. A steady streamlined flow. And the fluid must be non-viscous as well as incompressible. It must be incompressible. So this is a full theory part they want us to write down before entering into the question. So this explains everything about the Bernoulli's equation. Right, so let's get into the question and let's see what they ask afterwards. During heavy wind, sometimes roofs of closed buildings are blown off. Use the Bernoulli's equation to explain this phenomenon. Right, so this is another theory part. So we are going to use Bernoulli's equation to explain this phenomena that they have mentioned. Right. So they also says that use the Bernoulli's equation to explain. So we'll have to draw a diagram explaining everything and also use the equation for this. So let's first draw the diagram for this. Here I have drawn the diagram. You can see that the streamlines I have drawn above the house. So the area of cross section is going to reduce as the wind goes from the top of the house. Right, so this is something that you have to do in your paper. So velocities I can mark here as v1 and here as v2. Right. So also you know the velocity of wind inside the house is 0, so there is no velocity. Right. Here I have considered 2 points A and B, just above the roof and just below the roof. Right. So in the explanation I can write that the speed of airflow just below the roof is negligible. So we can apply Bernoulli's to A and B. So let's apply PA plus half rho u squared PA plus half rho V2 squared is equal to PB plus 0, because on that side there is no pressure due to the flow, and also there is no height difference. Right. So we can assume that A and B are at the same level. A and B are at the same level. Right, so the pressure difference we can get that PB minus PA. From this you can see that PB is greater than PA is half rho V2 squared. This is the pressure difference, right? So you can get the pressure difference and multiply that by the area. So we can say area of the roof if it's capital A, then you can say the force acting on the roof force acting upwards on the roof is equal to PB minus PA into A. Half rho A V2 square. This is the force acting upwards on the roof. So we can write when this force is greater, roof may blown off. Right, so this is what they expect you to do. They expect you to write a full explanation about what happens here. So this is why in Bernoulli's we learn about these examples or the applications of Bernoulli's, right? Okay, so let's get back to the question and let's see what they ask us. A narrow stream of glass blows out a gas jet in the horizontal direction. In order to measure the speed of the gas at the outlet of the jet, a student uses a U-tube which is open at both ends containing an oil. When U-tube is held vertically and close to the outlet so that only one of the ends is in the stream of gas, he notices a difference of 2.4 centimeters between the oil levels of the U-tube. Find the speed of gas at the outlet of the jet. Right, so for this also we need to draw a diagram, a proper diagram to explain how it works. And this is how you can draw the diagram. So one end of the U-tube is connected to the airflow here. So at that position, you know when the velocity is high, the pressure is low, so that level of oil has to be higher. So the difference is 2.4 centimeters. Now we can apply Bernoulli's to this scenario. So you can see that I have considered 3 points: A inside the tube, B outside when it's outside, C here at this position of the tube. So apply Bernoulli's for the airflow at point A and point B. So you know at point A, we can write the pressure is PA plus half rho V squared, and at B there is no flow, so it's just PB, or we can also say it's the atmospheric pressure. So here we got one equation. And guys, also you know that PB and PC, those two pressures are atmospheric pressures, so they are the same. So you can say also PB is equal to PC. Therefore you can say that PA plus half rho V squared is equal to PC. So PC minus PA is equal to half rho V squared. Right, so I'm going to take another point. Let's call it point D. Point D. So at this point D, you can see that we can say that pressure at point D is equal to pressure at point C. The reason for this is the same liquid, same level. So you need to write this as well, right? So we can write PD value. PD is equal to PA plus rho gh, or h rho g we can say. That is 2.4 centimeters over 100. Rho means 800 into 10. PC is equal to, we can just write that as PC. And PC minus PA, we have found a value here. So you can put PA onto this side and write 2.4 into 80 is equal to half rho V squared. Rho of the gas is 1.2 and V squared. So you can simplify this. Once you simplify this using a logbook, you will get 17.9 meters per second for this. Part 2 in the question is saying if the area of cross section of the gas stream at the outlet is 10 to the power minus 4 square meters, find the rate of mass flow of the gas in the stream. The rate of mass flow, right? So they have given the area of cross section of this one. It is 10 to the power 4 minus 4 meters square, and they want us to find the rate of flow, rate of mass flow. So we can write the rate of mass flow. The rate of mass flow is equal to the rate of flow. The rate of flow multiplied by the density. You know the rate of flow's units is volume per second, and density is kilograms per meter cube. So when you multiply these two, what you get is kilograms per second, right? And you know the units or the equation for the rate of flow is AV. You multiply the cross-section area from the velocity and you multiply it by the density. So it's AV rho, right? So you can substitute the values now. Velocity we have found in the previous, it's 17.9. 10 to the power minus 4 into 17.9 into the density of the gas is 1.2. So you get 2.15 into 10 to the power minus 3 kilograms per second. This is the answer for part 2. Right, let's go to part 3 as well. So in part 3, they're asking calculate the power of the gas jet. The power, right? You know, power is work done per unit time. Work done per unit time. So every second you can see that it is emitting this much of mass with a velocity of 1.79 as we found here. So every second it's going to emit this much of gas with a velocity of 17.9, not 1.79, 17.9, right? So how do you write the power? So we'll first write an equation for this. Power, you can write the rate of mass flow. Rate of mass flow, that's the mass per second, multiplied by the velocity or the speed into half. You have to multiply this by half. So it's kinetic energy. half into mass per unit time multiplied by not speed squared. So it's half mv squared equation. So you can write half into rate of mass flow. We just found out that is av rho into v squared. So the equation is half a rho v cubed, half a rho v cubed. What you get from this is 0.34 joules per second or 0.34 watt. So this is how you do question number 2, part A.